Howdy, my name is Logan Fitzgerald, and this is our group's presentation on rocket propulsion. This is our group. So, in rocket propulsion, it all started around 12th century China, where the Chinese developed rocket-propelled arrows. In chemistry and engineering today, we have developed that into all the fuels and means of transportation through the cosmos. With every scientific advancement, we draw closer and closer to discovering what we share our galaxy with.
Howdy, I'm Daniel Stinson, and like Logan said, rockets started with solid fuel. It started with the Chinese rocket-propelled arrow, however it fell to liquid fuel because of lack of efficiency. However, technology nowadays has improved, and we're now able to harness the expanding gases to produce more thrust. The solid fuel rocket is still in use today by NASA, the U.S. Air Force, and the U.S. Navy. The chemistry and physics behind solid fuel. The reaction between ammonium perchlorate and aluminum powder is massively exothermic and produces lots of gas and heat. The gases are forced through a small pinch in the motor, causing gases to accelerate, similar to putting your thumb over the end of a garden hose.
Liquid-fueled rockets work similar to solid-fuel rockets. However, liquid fuels require oxidation, usually from a separate chemical, and some liquid fuels include liquid hydrogen, gasoline, kerosene, alcohol, and nitrogen tetroxide. They can be divided into two parts. A monopropellant is just by itself as a neon oxidizer. Bipropellants require liquid oxygen or some other form of oxidizer in order to ignite. And they can be divided into hypergolic or non-hypergolic. Hypergolic, they can burn on contact with the oxidizer, and non-hypergolic, they require an outside ignition source.
Hi, I'm James Gumper. A cold gas propulsion system is unlike a solid or a liquid fuel gas propulsion system because it is obviously gaseous. Propellants include hydrogen, helium, nitrogen, ammonium, and carbon monoxide. Okay. The way it works is gas is chilled to make its volume smaller so you can get more of it into a container, and then that can be heated up or pressurized so to create a lot of thrust.
Hi, I'm Anthony Bake, and I'm here to describe the ion propulsion system to you. The ion propulsion system is NASA's newest propulsion system. This is where xenon is pumped into an ionization chamber, so is electrons. The electrons are supposed to hit the xenon atoms and break off. That'll create a positive xenon ion, and that'll force the xenon ions to go through this positively electric charged fence, and that'll cause the xenon ions to accelerate towards the negatively charged fence and shoot out the rocket. That'll help it propulse. These are supposedly these ions are going to be sped up to speeds of 90,000 miles per hour out of the ion thrusters, and they all need neutralizers at the end to spit out more electrons to equalize the exhaust in case of the spacecraft having to build up a negative charge and causing the ions to come back in. This is the past, present, and future of ion thrusters. First ion test in space was July 20th, 1964, and they've currently been using them all throughout different communication satellites, up to 100. And there's 3 ion thrusters on the newest NASA satellite, the Dawn, which is currently going into deep space. For the future, NASA's currently developing two different types of ion thrusters that'll be cheaper, more powerful, and reduce complexity for their deep space travels.
This was our presentation on rocket propulsion. I hope you found it very interesting, and
Thanks,
Diego.
Diego.